Okay, in this segment we're going to start talking about the MOS transistor, or the metal oxide semiconductor transistor. And what we're showing in this series of slides is something called the MOS structure, and we're going to consider the electrostatics of this structure. So um, normally this is rotated 90 degrees counterclockwise from the orientation I'm showing it here. This red area here, shown on the right, is the M in the MOS. It's the metal. And historically, when MOSFETs were first made, this was aluminum. This electrode here, or this part of the structure, was made out of aluminum, and this is typically called the gate. In more modern processes, this would be made out of a polycrystalline silicon. So the main silicon substrate is a single crystal silicon, and polycrystalline silicon is a deposited silicon that has many little tiny grains of silicon crystal with sort of different crystal orientations relative to each other. So it's kind of a less regular structure than the silicon, which is down in the bottom here. But this is doped to a very high level of doping so that it is basically metallic. So this is the M in the MOS structure. This little void area in here, this little thin area, is meant to be the O, the oxide. So this is silicon dioxide typically, and that is a very good insulator. And it grows natively on top of silicon. So if you take silicon and you put it in an oxygen ambient and you elevate the temperature, you get a small thin oxide growing natively on top of the silicon. And that's really one of the magical things about silicon, is that it has an oxide that grows on top of it that is matched with the lattice of the silicon, and it comes for free. And that's really one of the beauties of silicon, and that's why it came to be the main semiconductor material that we deal with in modern electronics. And then you have the silicon, which is down here. So I mentioned that this electrode is usually called the gate, the M, and this part of the structure, which is the silicon, is typically called the body or the bulk. Okay, those are the substrate sometimes. So in this particular structure, we are envisioning a lightly doped P-type substrate, which we're going to be imagining that we're connecting to ground, and then we're applying voltage to the gate with a voltage source here. And what we're going to do is we're going to consider a sequence of gate voltages that we're going to apply. We're going to consider what the energy landscape looks like for an electron as we go through this structure. Now remember, this would be normally the top surface of the silicon right here. The right edge of this yellow block would be the top surface of the silicon substrate. And then this little thin layer of oxide sits on top of that, and then the gate sits on top of that. We've rotated it here by 90 degrees clockwise so that we can really draw this energy landscape picture in the vertical direction conveniently. But normally when we draw a cross section through one of these transistors, normally it would be oriented 90 degrees relative to what we're seeing here. Okay. So the particular gate voltage we're starting out with here is called V flat band. FB stands for flat band, and it's basically a zero condition. The flat band voltage is just defined to be the gate voltage that makes the bands, the energy bands. Remember, this is sort of the conduction band edge, which is the lowest energy that a mobile electron can have, flat. So if we start out down here in the substrate and we go all the way up to the surface, the band is flat. Inside the oxide, there's no electric field, so it's flat here. And this is a conductor, so it's basically flat all through the conductor. And so this is kind of our zero condition. Now, the flat band voltage is not exactly zero. It's usually kind of plus or minus, within the range of plus or minus 50 millivolts relative to zero. But it represents kind of a zero condition. This energy barrier that exists when you go from the silicon to the silicon dioxide, which I mentioned was an insulator, is very, very, very tall. And so I've drawn these little squiggle lines here to represent the fact that this is a very, very tall energy barrier. To give you a sense of scale, the height of this energy barrier between the silicon and the silicon dioxide is about 3.2 electron volts. And the average energy that an electron would have due to just thermal energy, its motion due to the fact that it's got some finite temperature and it's banging around with the lattice, would be kT, which is 25 milli-electron volts, or 1/40th of an electron volt. And so 3.2 electron volts of energy represents basically 3.2 times 40, which is, 40 times 3 is 120. 0.2 times 40 would be, what, 8? So it's like 38 times the average energy of an electron. And so the Boltzmann distribution would be e to the minus some incredibly huge number, 3.2 divided by 0.025. That would be the multiplier on the number of electrons that have enough energy due to thermal energy to get over this barrier. So it's just not happening. It'd be like you standing at the bottom of a tall skyscraper and saying, I'm going to jump over the skyscraper. And it's just not going to happen. Normally the electrons can't surmount this energy barrier. And so we basically want to see what's going on here at the top in this picture, but we can't really draw it to scale. So we have these little squiggled lines here, which represent the fact that there's a little bit of a break here. And we're just showing the top here, the top end, and this is not to scale. Anyway, so we're going to imagine increasing the voltage on the gate relative to flat band. And what that's going to do is to put some positive charges on the gate. Right? To raise the voltage here above flat band, we have to put some positive charges on the gate. They're going to send out their field lines and basically repel some of the mobile holes that are in the substrate here near the surface. And it's going to create a little depletion region. So we're going to send the holes away. They can move, and they don't like to be up near these positive charges, and so they're going to move away, and that's going to uncover some of these ionized acceptors. Right? So these are fixed space charges that have a negative charge, and those will balance the positive gate charges and create a little depletion region underneath the gate. And so what we'd like to do is the same kind of thing that we thought about when we thought about the electrostatics of the p-n junction here. We're going to imagine using Gauss's law to integrate the unbalanced charge density up to the surface and to get the electric field. And then we can integrate the electric field to get the potential profile. And so back here in the depth of the substrate, there is no unbalanced charge. It's all charge neutral. There are as many mobile holes as there are ionized acceptors per unit volume, and so it's all charge neutral. And so the charge density is 0 up until we get to the depletion region, in which case we start seeing a minus n sub a as our charge density, because n sub a is the acceptor concentration. Okay, so it's constant. That's our typical assumption here, until we get up to the surface. And so If we integrate 0, we get 0. Then we integrate a constant, we get a ramp. And so we go from 0 to something that looks like a ramp with distance up until we hit the surface. And then we change to a different type of material. So we go from silicon to silicon dioxide. And it turns out that the electric field boundary condition when we cross a dielectric is something we talked about when we put up those three basic relationships of electrostatics, and I said it was sort of related to Snell's law, but the product of the electric field times the permittivity of the material is conserved across this boundary here. So the permittivity of silicon dioxide is about 3 times higher than the permittivity of the silicon. And so basically whatever the electric field is when we get to the edge of the silicon here, we multiply by roughly 3 to get the slope, or to get the electric field in the silicon dioxide. And then what we do is we integrate that a second time, and so we're integrating 0 up until this point, and then we start integrating a ramp, which gives us a parabola. And so what happens here is that the bands are flat, but then we get to the depletion region, we start to get a bending of the bands down here. And this is a parabolic shape. And so the relationship between the potential here at the surface, this little minimum value here before we hit the insulator, is called the surface potential, the potential at the surface, which is typically denoted psi sub s, as shown right here. That would be related to the square root, or the distance is going to be related to the square root of the surface potential, right? Because this is a parabola, so x is equal to psi sub s squared, so x is going to be the square root of psi sub s. So there's a monotonic relationship that holds between this depletion region depth and the surface potential relative to the 0 level here deep in the substrate. Okay, so just bear that in mind. There's a monotonic relationship, it's a square root relationship between the surface potential and the depth of the depletion region here. And so if we increase the voltage on the gate higher still, we're going to deplete a little bit further down into the substrate. Put more gate charges here. We're going to send more positive holes away and uncover more space charge, creating a wider depletion region, or a deeper depletion region here. And that's going to have the effect of bending this band down a little bit further. And so what we're doing here is we're creating a little notch here right at the surface where there's a local minimum of energy for an electron. And if we continue this even further, we get more bending of the bands, a wider depletion region. And if we were to imagine creating an electron hole pair in this depletion region, let's think about what happens, right? So we create an electron hole pair. This could be by thermal generation, or there could be some sort of photon that comes in here and gives us an electron hole pair by optical generation. And this electric field that exists here is going to be such that the hole is swept into the substrate, and the electron is going to want to go toward the surface. It's going to be attracted to these positive gate charges. And so what will happen is that this electron will hit this oxide. It literally runs into a glass ceiling. So normally this is oriented vertically, right? So that this silicon dioxide, which is basically glass, is oriented horizontally. And this electron basically zips up to the surface and hits that glass ceiling, and it sticks there. just stays there, right at the surface. And you can see that this charge here had been terminating its field line on this ionized acceptor down here deep in the depletion region. But it's just as happy to terminate on this mobile electron that we created, and that narrows the depletion region just a little bit. The hole that we pushed away here is an extra hole that gets collected as a little bit of current flowing out of the bulk terminal here. And so we have a situation where we have this little low spot in the energy landscape where an electron can sit in that little notch. Okay, so if there's an electron that kind of comes in here, it's going to want to sit up in that little notch, that little low spot of energy. Okay, so that's the MOS structure. This is called the two-terminal MOS structure, where we have the bulk and the gate. And now what we're going to do is we're going to move on to consider something called a three-terminal MOS structure. Okay, so what we're doing here is we're imagining the same sort of MOS structure we had in the last sequence of slides, and we're also putting at one end of this structure a p-n junction. Okay, so here we have a heavily doped N+ region, and we have our lightly doped substrate. And if you think about sort of this little area up here, this is the thing we talked about before. We talked about the p-n junction. Down here, this is what we talked about in the last few slides. Okay, now we're going to be interested in what happens when we put this p-n junction near this MOS structure here. And this is actually called a three-terminal MOS structure because we have here the gate, we have here the bulk or the body, substrate, and here we have this N+ region, which would be basically like the source. It would be called the source. Well, we're imagining the gate is at flat band. Okay, so there's no depletion region beneath the gate, and the bands are flat all the way up to the surface here. And then around this p-n junction in all directions, we have the built-in potential, which creates an energy barrier, and we have a depletion region. Okay, so electrons in here in this N+ region would want to diffuse into the region of relatively low electron concentration in the p region. Likewise, holes, which are relatively plentiful in the p region, but relatively poor in the n region, would want to diffuse this way toward the region of low concentration. And we wind up creating this depletion region here, this devoid of mobile carriers, where we have these exposed space charges creating an electric field which opposes the diffusion of these carriers down their concentration gradients. Okay, so we have this built-in potential, which we talked about before. And so the electrons kind of stay in this N+ region, and the holes stay in this P- region. Okay, so now we're going to imagine a sequence of increases to the gate voltage above flat band and consider what happens. Well, we start to increase the gate voltage above flat band. We put a couple positive charges here on the gate, and we start creating a depletion region just like we did before underneath the gate. This depletion region starts out at zero width and starts to increase, but it's at the beginning much less thick than the depletion region, let's say underneath the N+ region here. Okay. We continue this, and we put more gate charges on. We deplete down a little further. At some point, this depletion region, which is increasing monotonically as we increase the gate voltage, has to become the same depth as the depletion region underneath this N+ region. Okay? Now, that's a very interesting point, because if you recall what we said, the potential difference across the depletion region is going to be monotonically related to the thickness of the depletion region. Okay, so the potential drop from the substrate to the surface here is encoded in this nonlinear monotonic relationship, the square root relationship, to the potential drop. And so when the depletion region underneath the gate gets to be the same width as the depletion region underneath the source here, underneath this N plus region, then that means that the built-in potential is the same as the built-in as the surface potential here. And so there's practically no difference, or how shall I say this, there's practically no energy barrier for electrons to go from this N plus region where they are happy into this low energy region, this notch of low energy that we've been creating by moving gate charges up here and creating this depletion region. Right? Remember, so we bent the bands down, so there's a nice low energy region here. You can imagine that once we do this enough, we reduce the potential here to the same point as it is inside this N plus region. In which case there's no energy barrier for the electrons to get up into this region here at the surface, which is called the channel. So every additional gate charge I put on the gate above that point or beyond that point goes into being balanced by additional mobile charges that we drag from the N plus region into the channel region. Okay? So let's go through that again. So here we have this energy barrier that the electrons see uniformly in all directions, which is the built-in potential of this p-n junction. So they're not going to go into the p region in any direction. But when we first start adding gate charges, we start sending the holes away, and we start creating a little bending of the bands here up to the point of the surface where we get kind of a low spot in the energy. But the bending of the bands is not very much at the beginning. And so there's an energy barrier to get from the source region, this N plus region, up into this area right at the surface, but it's not quite as big an energy barrier as it would be to get back into the substrate through this route, but it's still a pretty large energy barrier. But as we add more gate charges and we increase the width of this depletion region, we bend the bands down a little bit more, and we reduce the energy barrier here by more and more. And eventually, when this depletion region thickness gets to be the same as this depletion region thickness, then we've bent the bands to such an extent that there's practically very little energy barrier for the electrons to be able to get up into this surface region here, which is called the channel. And then after that point, every additional gate charge we put in will wind up terminating on a mobile carrier instead of depleting further down into the substrate and being terminated on a a fixed space charge, an ionized acceptor. So this voltage on the gate at which this condition occurs where we get these equal width depletion regions is called the threshold voltage, which we denote by VT. We use UT for the thermal voltage and VT for the threshold voltage. That's why we use U for the thermal voltage, to distinguish it from the threshold voltage when we get to MOSFETs, in case you're curious about that. But the idea here is that the initial gate charges that we have to put in go into creating this channel region. And once we get up to threshold, then basically every additional gate charge winds up dragging in a mobile charge, and the depletion region doesn't get any thicker. The depletion region underneath the gate doesn't get any thicker beyond that point. And so there's a couple of things to note here. We call this range of gate voltages between flat band and threshold subthreshold. Okay, this is the region of gate voltages where we're basically creating this depletion region, bending the bands down, and creating a nice low energy spot up at the surface. There will be a few mobile electrons in the channel, but they're very, very small in number compared to the number of bulk charges here, the number of space charges in the depletion region. They're very, very small in number compared to these. Then, once we get up to threshold, beyond that point we're above threshold, and the number of mobile charges here, let's say per unit area, in the channel winds up being potentially in excess of the number of mobile or number of ionized acceptors in the depletion region per unit area. And so we have sort of 2 or 3 regions depending on how you want to parse it. We've got subthreshold, which is the gate voltages below threshold, where we're creating the depletion region. And we have what we might call a little band around threshold or perithreshold, where we're kind of 50-50 with respect to the mobile charges versus the bulk charges here, the depletion layer charges. And then once we get a little bit above that, we're in what we call above threshold, where the mobile charges will potentially greatly exceed the bulk charges or the depletion layer charges. And so we talk about subthreshold, perithreshold or around threshold, and above threshold. We can also talk about the sort of regions of operation or qualitative regions of operation in terms of something we call inversion. Okay, so to talk about that, or to explain that, we start out here at flat band, and the area, the semiconductor type underneath the gate here is basically P, right? So we've got mobile holes which have positive charges right here underneath the gate. And so we start out P-type, but then because we're putting these gate charges on and sending the holes away, we create this depletion region. And by the time we get to above threshold, our mobile charges here at the surface have inverted their type, right? So instead of being holes, they're electrons. And so we say that there's been, due to this field from the gate charges, there's been an inversion of the type of mobile carriers. And so this is called sometimes the inversion layer. Right here at the surface is basically a 2D sheet of mobile charges that counterbalance the charges on the gate that we've put on in excess of the threshold voltage. And so we could talk about the level of inversion, and it's compared to basically the original density of holes in the region here. Okay, so you can parse it out in terms of the charge, the mobile charges here in the gate per unit area relative to the number of ionized acceptors per unit area underneath the gate. The ionized acceptors have the same density as the hole density because basically these holes came from the ionized acceptors to begin with. And so when the number of electrons in the channel is few in number compared to the ionized acceptors in the depletion region, we say that that's weakly inverted. So we've got some opposite type of charges, mobile charges here at the surface, but their density relative to the ionized acceptors is small. And so that's called weak inversion, and that correlates with subthreshold operation. And when we get to this crossover point here where the number say the number of mobile carriers around threshold is equal to the number of ionized acceptors per unit area, then we're basically at moderate inversion. So when the two are comparable to each other, that is called moderate inversion, and that correlates with around threshold or peri-threshold. And then strong inversion is when the density or the number of mobile electrons in the channel, in the inversion layer, greatly exceeds the density or the number of ionized acceptors per unit area in the depletion layer. So that's called strong inversion and correlates to above threshold in terms of the threshold language. Okay, so we have weak inversion being synonymous with subthreshold. We have moderate inversion being synonymous with peri-threshold or around threshold. And then we have strong inversion, which is correlated with above threshold. Okay, so remember, the threshold voltage is basically just a special gate voltage at which the depletion region depth here underneath the channel first becomes equal to the depletion region depth underneath the source region here, so that there is practically no energy barrier between the source and the channel region here at the surface. And that being the case, it's more energetically favorable when we add an additional gate charge to drag more electrons in to counterbalance those gate charges than it would be to make the depletion region thicker. Okay, so that's all we're going to do for this segment. We'll talk about the structure of the MOS transistor and start to talk about where the terminal current voltage characteristics come from in the next segment. So we'll finish up the last couple of slides next time and then get into subthreshold operation or weak inversion operation. Okay, that's it for now.